Hi everyone, I'm Minhao Chen. I'm glad to present our paper, SHAP-EDITOR, Instruction-Guided Latent 3D Editing in Seconds. This work is done by me, Junyu Xie, Professor Iro Naina, and Professor Andrea Vadaldi at the View Geometry Group at the University of Oxford. I will present our paper in the following aspects. First, I will talk about the background, motivation, followed by the preliminary knowledge, and then I will present the detailed methods, some results. At last, I will show some limitation and future work. Recent breakthrough in text-to-3D generation has drawn great attention in our community, such as Dream Fusion, Polyfic Dreamer, Fantastic 3D. Also, 3D editing with text instruction is also possible with the help of the powerful 2D priors such as diffusion models or clip model. Here are some examples of 3D generation and 3D editing methods. However, existing text-to-3D approaches are heavily based on test time optimization, which requires at least tens of minutes and even hours for generating a simple 3D object. So the question is it possible to avoid such cost? Can we do 3D generation and editing in the latent space? Can that be a solution? So recently, OpenAI proposed SHAP-E, a 3D generation framework which produces 3D implicit function through diffusion in the latent space. Here are some examples of the generation of SHAP-E. Inspired by the idea of SHAP-E, in this paper, we present a method called SHAP-EDITOR aiming at fast 3D editing. We propose to learn a universal editing function that can be applied to different objects within 1 second. Now let me talk about some preliminary knowledge about SHAP-E. There are two important parts in SHAP-E. The first is its autoencoder network. The input of the autoencoder network is point cloud and different renders. Then it will output a latent, and this latent can be further decoded into different implicit 3D functions such as signed distance function or nerf. The second part is the latent diffusion network for 3D generation. Given a random noise and text or image condition, the SHAP-E's diffusion network can then generate a latent, and this latent can be further decoded into signed distance function or nerf for 3D generation. Another important technique we used in our paper is SDS, score distillation sampling. SDS is a method that's proposed by Dream Fusion. It can distill 2D priors to a 3D parametric network such as nerf. However, in this work, we try to distill knowledge from 2D diffusion models into a 3D editing function instead of just one 3D representation. Now let me talk about the method part. The inference of SHAP-EDITOR is very simple. Given a 3D object, we first encode it into a latent with a frozen SHAP-E encoder, and then we pass it into a network with editing instructions such as add a party head to it. And then this network will produce an edited latent that can be decoded into a nerf. The question is how we can train such a network. Inspired by Dream Fusion, we try to distill knowledge in 2D editors into a 3D latent network. Given a 3D object, we encode it into a 3D latent and feed into our SHAP-EDITOR network to get an edited latent. This edited latent and the original latent are then decoded into nerfs. These nerfs are then rendered with the same viewpoints. At last, a SDS-like loss is applied for supervision. We also find that distill only from one network is not enough for 3D editing. 2D editing networks such as Instruct, Pix2Pix, Magic Brush cannot perform significant geometry change to the images. 2D text-to-image networks such as Stable Diffusion, they cannot maintain the original structure and the appearance. So we try to distill from multiple 2D priors. We're also classifying editing into two types, local editing and global editing. We use different laws and different pairs for different editing. For global editing, we mainly distill knowledge from 2D editing networks such as Instruct, Pix2Pix, and Magic Brush. For local editing, we distill knowledge from text-to-image models such as Stable Diffusion. Now let me show you some results of our SHAP-EDITOR. I will first give some comparison with state-of-the-art models, both quantitatively and qualitatively. And then I will show you some additional results on global editing and local editing. At last, I will give you some discussion about the interesting observations we find in our experiments. Here is a qualitative comparison between our method and other methods. Our method can well preserve the details of the original 3D object, while other methods either fail to follow the editing instruction or change the identity of the 3D object. Here is a quantitative comparison between our method and other methods, which achieve superior performance with over 1,000 times faster. In addition, we show that SHAP-EDITOR has great generalization ability. Even on unseen categories such as fox, deer, we can still apply these editings. Here are some visualization of global editing. We also show some results on local editing as well. During our experiments, we also found some interesting observations that we actually can control the effect strength of our editing. Additionally, we find that we can actually find an editing vector that can be applied to different objects and categories. We consider this is an interesting property of the SHAPE's latent space. Also, we find that our method can provide progressively editing, that we can first turn the deer into goat and also add a sand head to this goat deer. Now let me talk about the limitation and future work. For the limitation, first, the framework is heavily based on SHAPE, which limits the upper bound of performance and quality. Second, we cannot receive arbitrary text input. We have to train the text instructions and then in the inference we can use that instruction. For the future work, which will try to improve the performance of the SHAPE's framework, such as change the 3D decoder to generate the Gaussian splatting, or train another 3D autoencoder network ourselves. And second, we might scale up the prompt amount to achieve open vocabulary 3D editing. Thanks for listening. You can also check out our project website, codes, and the demo from the links above.